All right, I think the last one we left off on was this one here, right? Is more lamps are put into some kind of circuit. Yeah, let's look at the last two that we left off on, right? So as more lamps are put into a series circuit versus as more lamps are put into a parallel circuit, what happens to the current, right? You have to put a couple of ideas together. Do you guys remember the more lamps you put in series, that increases the overall resistance? And if you increase the overall resistance, doesn't that decrease the current? There's an inverse relationship going on here. You guys remember that? Okay. Remember too, like the more bulbs you put on in series, they become dimmer and dimmer and dimmer, right? Right. So there's less and less current flowing. Okay. Then the one we actually left off on last time was what if you put more bulbs into a parallel circuit like this? Do you guys remember every time you add on another bulb, the other bulbs maintain their own brightness. So it just opens up a new pathway for electricity to flow. Right? So the same voltage drop from one side to the other. Okay. So would that increase the overall current? Right? Or another way to think of it is that every time you add on a resistor in parallel, it decreases the total resistance. Right? And then if you decrease the resistance, you increase the current. Okay. Right. So you guys got that? If you put on more bulbs in series, that decreases the overall current. If you put on more bulbs in parallel, that increases the overall current. Okay. Number 84, when one bulb in a series circuit containing several bulbs burns out, what's going to happen? Let's bring up this picture again. Right, suppose you have the circuit right here, and then this bulb burns out. What's going to happen to the circuit? Does that open the circuit so that no electricity flows at all? Right? And then don't the other bulbs just completely turn off? Right? Isn't that exactly what would happen? Right, guys got that? Okay. Versus this question, when a bulb in when one light bulb, in a parallel circuit containing several bulbs burns out. Let me pull up that picture. That's this one right here. So like if this bulb gets knocked out, is there still a voltage difference across the other two resistors? Yeah, and it would also still be a closed circuit. There would be a closed loop here, there'd be a closed loop here. So won't the other bulbs just stay as bright as they were before? Same voltage drop across each of them, same resistance, right? Of course, you know, if you add the other bulb back in, the other two would also maintain their brightness, right? Would that be true? A short circuit occurs when, do you guys remember that? Oh, all right. Yeah. I've been cleaning up a little bit, so I don't have my batteries up here. But you guys remember I took a battery and took a paper clip. If you connect a paper clip to both leads of the battery, that creates this right here, or a short circuit. Isn't that when the positive's connected directly to the negative? Right? That's the best answer here. There are some other choices, and there's an all of the above, but let's just go with the positive connected directly to the negative. Okay. Positive touches the negative. The total resistance. There's a couple of questions of total resistance, but different types of circuits. This one, the total resistance of 10 ohms and 7 ohms in series. As series, should you just add the resistors up, add them up? So say 10 plus 7 is 17, probably there, right? Versus this question, you got 6 ohms and 12 ohms in parallel. In parallel. Should I treat this like guys painting a fence? Remember that math? Well, that analogy that has the same math behind it, right? Here, how about this? If it takes one guy 6 hours to paint a fence, another guy 12 hours to paint a fence, they make a two-man team. Do you think they can knock out the job in about 4 hours or so? Right. Let's try the product over sum method. Right. So if I do 6 times 12 over open parentheses 6 plus 12, right? Hopefully I get something a little bit less than 6 hours. See? Oh, it is exactly 4. So 4 hours to paint the fence, or in this case, like 4 ohms of total resistance. Notice there's less resistance overall than there is for either resistor. Kind of makes sense to talk about that. You know what? Just for completion, let me go up here and try the fraction method of this. So it could go 1 over, and then all this stuff. So let's try that. What's 1 over open parenthesis 1 over 6 plus 1 over 12. Okay. Hopefully it also equals 4. Yep, it's also 4. Right, using the reciprocal method. So there's 2 different ways to solve that one. If you break a bar magnet in half, what happens to each half? Well, I can demonstrate this right here. Right here, this could be a bar magnet, right? There's like a north pole here and a south pole here. Remember I told you guys the poles are like on these faces. If I break this in half, do I have two little magnets that each have their own north and south, north, south, north, south? Yeah, sure do, right? Hey, is there any such thing as a unipolar magnet? Can you have a magnet that just has a north pole and no south? No. Every magnet will have both a north and a south. And if you break it in half, it just becomes two smaller magnets. Right? So if you break a bar magnet in half, you get two small magnets. Okay. A device consisting of, okay, got a pair of questions here. First of these two says, okay, device consisting of a coil that is mechanically rotated in a stationary magnetic field. Okay, so we got here is got a magnet, we got a coil of wires, and there's a magnet that's forced past the coil of wires. Ooh, is that going to generate an electric current? Generate electric current? Oh, actually, we got it right here. Magnet, wires, force. Am I generating some electric current? Ooh, look at that, right? Generating electric current. And the follow-up question, a device that transforms electrical energy into mechanical energy. Okay, so now what if you take an electric current, run it past a magnet, and it creates a physical force? Ooh, kind of like a ceiling fan or anything with a motor in it, because that is a motor, isn't it? Like a motor, right? Okay, so if you take a force and force a wire past a magnet, that will generate an electric current. And if you take that current and run that past a magnet, that will create a force, and that device is called a motor. Okay. A motor and a generator might literally be the same device, just one's taking a force and creating a current, the other's taking a current and creating a force. Right? Just which way does the energy flow? Right? Most commercial generators are driven by do you guys remember the Rankine cycle with steam, like a steam turbine? Right. So like how do you get energy from coal or nuclear? Well, you boil water, turns into steam, steam turns a turbine that forces a wire past a magnet, create electricity. Yeah, so steam. Now, steam doesn't create all the electricity. You got hydroelectric dams, you got your photovoltaics, but yeah, most electricity is generated with steam. Right? Light behaves. Okay, now we're getting into future topics. Okay, so the only topic that we haven't covered yet that I need to go over with guys is quantum mechanics. So I'll tell you guys a little bit about this. I'll just give you guys these answers and then we'll go more into depth in the coming days. Light behaves as, okay, so is light a wave or is light a particle? Or is it both of the above? The answer I'm looking for here is both of the above, both A and B. This is called wave-particle duality, wave-particle duality. Right. So in physics, particles have certain properties, waves have certain properties. Forever they'd been seen as like two distinct phenomenon. Right? And then what was light? Well, for a long time this was one thing. No, maybe it's actually the other thing. But yeah, early 20th century physics, about 100 years ago, we're going with wave-particle duality. Right? Actually has properties of both. Okay? A photocell can be activated with a blue light, but not with a red light. Right? This is because the blue light, what? Right. Now, this is actually one of the examples of light having particle-like properties over wave-like properties. I mean, what light has both properties, right? You can do, for example, a double slit experiment. You guys are going to see it and show that, okay, well, light has wave properties, creates an interference pattern. But then there's this photovoltaic effect, which is the question we're on right now. Actually, this is something that Einstein got his Nobel Prize for. Like when you say, oh yeah, Einstein, of course, got Nobel Prize in physics, of course. It actually wasn't for relativity, which you would think it was, because that's what he's most known for. It was actually for the photovoltaic effect. So the answer here is because, okay, what was the difference between blue light and red light? Blue light has a higher what than red light? Oh, frequency, right? Higher frequency. You guys remember learning about electromagnetic spectrum, right? So just in the band of visible light, right, goes like Roy G. Biv, right? Red has the longest wavelength, lowest frequency, and like violet has the shortest wavelength, highest frequency. Okay. Right. So it turns out that the frequency is directly proportional to the energy that you can get out of light. It's sort of analogous to say if you filled a garden hose with marbles and you're watching the marbles flow out at a certain rate. Well, the marbles were flowing out more frequently, right? And each marble represented like an energy density, maybe like a photon. Then yeah, this is why light follows the particle model. Next question, the wavelength of a particle. Wavelength of a particle? How can a particle have a wavelength? So this is more wave particle duality, but now it's generalized to more than just light. This is called the de Broglie wavelength. Okay? So, and most of these questions are application type questions, like higher order type questions. But okay, this one's a little bit trivia, but good to know. You guys are gonna come across this anyway next few days. De Broglie wavelength. You can calculate this, and you can say, oh yeah, every particle actually has an associated wavelength, and the less mass the particle, the more pronounced wavelength it has, and that's when you get down to like subatomic particle size, right? Like for example, actually that leads straight to the next question: the discrete orbits of electrons. Discrete orbits of electrons. Here we go. Are best understood by considering the electrons what? Okay. So do you guys remember in chemistry learning about electron configuration? You guys remember that? Or why? You guys remember how most atoms have like up to 8 electrons on the outer shell, right? Like in all those noble gases, the outer shell is filled, and so they don't really want to react with anything chemically. Right? Well, why is that? Like, why is it that electrons like fit into like discrete orbits, and they can fit like 2 or 8 or 18 in the outer shell? Why is that? Well, it comes down to the wave properties of electrons. That's the answer to this question, by the way. The electron's wave properties. Okay? And here's an example of this. Right? Now, if you use the model of electron going around the nucleus of an atom, it's kind of like a planet going around the sun, something like that. Okay, well, that's a fine model up to a certain point, but that model breaks down. It doesn't tell you exactly like why exactly these discrete orbits. But if you think about the wave properties of an electron, you guys see how I have like 5 wavelengths going around here, like these 5 wavelengths. Right? And okay, well, you need a discrete number of wavelengths that the electron should fit around. It could be 4 or 5 or 6. It's kind of like adding on like paper clips. You can only add a discrete number. Okay, and that'd be a good explanation for why the electron can only fill certain like orbital shells. Okay, yeah. So these 2 questions are tied together, right? There's a de Broglie wavelength for an electron. That's why it can only fit into certain orbital shells. Last 4 right here. Nuclear fusion. Okay, we got fission and fusion. Okay, nuclear fission occurs when, you guys remember fission was taking very heavy elements like uranium or plutonium and breaking them into smaller elements, and then you get some energy out of that. Like there's a mass difference, and then that turn to energy equals mc squared. Right. Now this one has some weird answer choices. The one we're looking for here is the one that says electrical forces in the nucleus overpower nuclear forces, right? Because there's these 4 recognized fundamental forces in nature. 2 of them we've done a lot with in this class, so gravity and electromagnetism. There's also a couple of nuclear forces. There's something called the strong force and the weak force, strong nuclear force and weak nuclear force. Like if you've ever wondered, like why do all the protons hang out in the nucleus together? That doesn't really make any sense from electromagnetic point of view. It's like a bunch of north poles on a magnet. They all want to push away from each other. Okay? Well, there's this strong force that acts on a very, very, very tiny distance that will hold all the protons together. But if you can like break into that nucleus and have these electromagnetic force overpower the nuclear force, you can get fission. Very good part, right? Right. Nuclear fusion releases energy when we're talking about very light nuclei fusing together, right? Very light nuclei fusing together. Specifically, this is the next question, the primary fuel for a nuclear fusion reactor, fusion, is what fuel is used for fusion? Hydrogen. So that's like our sun, right? Our sun is a giant fusion reaction going on in space, right? Giant fusion reaction going on. Thermonuclear bomb, that's a fusion bomb, that's hydrogen. And there's never been a hydrogen bomb used in war, but just for like experimentation, right? That's like hundreds of times more powerful than those old fission bombs. And for nuclear energy, this is the technology that we haven't quite cracked yet. That might be like 10, 15 years away from being able to crack this one. But when we do, it'll like solve all our energy problems, or at least in the year 2022. seems to be the case. You know, maybe we'll get there like, so open up some new things we didn't know about. And last question, a nuclear process that has relatively few radioactive byproducts, okay? Because we do have nuclear power plants, but they're all fission plants, right? And then one of the problems with fission plants is you get all this radioactive waste. Well, you know, how do you store this? What do you do with it? It's going to be around radioactive for tens of thousands of years. But what process actually does not have all this radioactive byproduct? Fusion. Yeah, so fusion is even cleaner than fission is, right? So fusion. There you go. All right. You guys got this? That concludes exam review.